Nothing in the universe moves faster than light. That's the rule. Einstein said it, a century of experiments confirmed it, and every physics textbook on the planet repeats it. 300 million meters per second. That's the cosmic speed limit, and it applies to everything. Rockets, radio waves, you, me, all of it. Except, in March of 2026, a team of physicists published a paper in Nature, one of the most prestigious scientific journals in the world, showing that they'd measured something moving faster than light. Not in theory, not in a simulation, in the lab, and the thing that broke the speed limit, darkness. Now, before you start planning your faster-than-light vacation, there's a catch, and it's a big one. But to understand the catch, you first need to understand the discovery. And to understand the discovery, we need to talk about what light actually is when you look closely enough. We all know light behaves as a wave. Peaks and troughs, crests and valleys, oscillating electromagnetic fields rippling through space. When two beams of light overlap, their waves interfere with each other. Where peak meets peak, you get brighter light. Where peak meets trough, they cancel. You get darkness. And at certain very specific points in that interference pattern, the cancellation is perfect. Total. Absolute. The wave amplitude drops to precisely zero. Not dim, not faint, zero. These are called phase singularities, but you could think of them as dark points. They're tiny pockets of absolute darkness embedded inside a field of light, holes in the fabric of a wave. Here's a way to picture it. Imagine a whirlpool in a river. Water spins around a central point, but right at the very center, at the axis of the vortex, the behavior of the water becomes undefined. You can't really say it's flowing in any direction. That center point is singular. An optical vortex works the same way. Light energy spirals around a core, and at that core, there's nothing. Perfect, absolute, zero-intensity darkness. The phase of the light, which direction the wave is pointing, becomes meaningless. These dark points aren't a new idea. Back in 1974, two physicists at the University of Bristol, John Nye and Michael Berry, published a paper called Dislocations in Wave Trains. Nye had been studying ultrasonic pulses bouncing off rough surfaces and noticed something peculiar. The resulting wave patterns contained defects, dislocations, directly analogous to imperfections in a crystal lattice. He and Berry worked out the mathematics and showed that these singular points are a fundamental feature of any wave interference pattern. They're not bugs, they're built in. Then Berry took it further. By 1978, he'd calculated the statistical behavior of these dark points in random wave fields. And his math predicted something deeply strange. The speed at which dark points move through a wave field could, under certain conditions, exceed the speed of light. Particularly right before two dark points of opposite charge collide and annihilate each other. He and his student Mark Dennis refined this prediction in 2000, but for decades nobody could test it. No instrument on Earth was fast enough or precise enough to watch a dark point move. So here's where the story shifts. For 50 years, this prediction just sat there, a mathematical curiosity with no experimental confirmation. The problem was brutal. You needed to track features smaller than the wavelength of light itself, on timescales shorter than a single oscillation cycle of the wave. That's like trying to photograph a bullet by using a camera whose shutter speed is slower than the bullet. It can't be done unless you build a fundamentally different kind of camera. Enter Ido Kaminer, a professor of electrical and computer engineering at the Technion Israel Institute of Technology in Haifa. Kaminer is a third-generation Technion alumnus who did his postdoc at MIT, where he helped pioneer a field called free electron quantum optics, using free electrons as quantum probes of light fields. His Ad Quanta lab at Technion has spent years building an ultrafast transmission electron microscope that doesn't look at light directly. Instead, it fires incredibly short pulses of electrons through the electromagnetic field of a light wave and reads how those electrons gain or lose energy. That energy change maps the light field's amplitude and phase with extraordinary precision. How precise? The instrument achieves a spatial resolution of about 20 nanometers. That's roughly 10 times smaller than the wavelength of the waves being measured. And a temporal resolution of about 3 femtoseconds. That's 10 times shorter than a single oscillation cycle. To put those numbers in perspective, over 800 femtoseconds, the team captured 285 time-resolved frames, tracking roughly 50 dark points per frame across a field of view 21 micrometers wide. This gave them enough data to build real statistics on how dark points move, interact, and die. But there was one more clever piece to this experiment. Instead of studying dark points in ordinary light traveling through free space, the team studied them inside a thin crystal of hexagonal boron nitride, a layered material where light couples with lattice vibrations to form hybrid excitations called phonon polaritons. These polaritons travel about 100 times slower than light in a vacuum, and that slowdown, paradoxically, amplifies the superluminal effect. It's like shrinking the racetrack so that even a modest sprint crosses the finish line faster than you'd expect. So what did they find? Of all the dark points they tracked, 29% were moving faster than the speed of light. Not faster than the polaritons around them, faster than light in vacuum. The average velocity of the dark points came out to about 1.04 times the speed of light. In free space light, Barry's theory predicted only about 0.4% of singularities would appear superluminal. By using HBN polaritons, the team amplified the effect roughly 72-fold, making it unmistakable. And why does this happen? It comes down to geometry. When two dark points of opposite topological charge, one spinning clockwise, the other counterclockwise, approach each other to annihilate, their space-time trajectories form a parabolic curve. Position scales as the square root of time. That means velocity, which is the rate of change of position, scales as 1 over the square root of time. As the moment of annihilation approaches, that denominator drops toward 0, and velocity shoots toward infinity. The dark points don't gradually speed up. They accelerate without limit in the final moments before they wink out of existence. This is also where the team discovered something the community hadn't expected. Physicists had long noticed that the spatial distribution of dark points in a wave field looks remarkably like the arrangement of particles in a liquid. They have preferred distances from each other, just like atoms in water. But the velocity distributions are nothing like particles. No particle accelerates toward infinite speed right before it interacts with another particle. The analogy, it turns out, was only skin deep. Dark points obey different rules. Now the crucial question, does this break Einstein's theory of relativity? No, not even a little. Einstein's speed limit applies to things that carry energy, mass, or information. A dark point is none of those things. It's a geometric feature of the wave pattern, the location where peaks and troughs happen to perfectly cancel. It's like sweeping a laser pointer across a distant wall. The dot can zip across faster than light, but no thing is actually traveling. No energy is transmitted, no signal is sent. The same is true for the intersection point of closing scissors, or the shadow of a spinning object. Phase singularities belong to this same family. They're patterns, not particles. The paper lists 19 authors across 9 institutions in 5 countries. The co-first authors are Tomer Bucher and Andrei Gorlach, PhD students at Technion. Collaborators include researchers from ICFO Barcelona, the University of Milano Bicocca, Stanford, Harvard, the Shanghai Institute of Optics, and Kansas State University, among others. The boron nitride crystals were prepared by Hanan Herzig-Schoenfuchs at Bar-Ilan University. The work was supported by the European Union's Horizon 2020 program, the Gordon and Betty Moore Foundation, and Technion's Helen Diller Quantum Center. So why does this matter beyond the sheer coolness of it? Because phase singularities aren't just an optical phenomenon, they appear in every wave system. Quantized vortices in superfluid helium, Abrikosov vortices in superconductors, dislocations in ocean wave fields, nodes in quantum mechanical wave functions. If the divergent velocity behavior near annihilation holds across all these systems, and the mathematics strongly suggests it does, then Kaminer's team hasn't just measured something about light. They've uncovered a universal law governing how topological defects behave in all waves, everywhere. There are practical implications too. The 20 nanometer, 3 femtosecond measurement capability the team developed is a tool, not just a result. It opens a window onto nanoscale processes in physics, chemistry, and biology, phase transitions, charge density waves, ultrafast chemical reactions at their natural length and timescales. And in photonics, understanding how dark points move and interact inside two-dimensional materials could feed directly into designing better quantum communication channels, super-resolution imaging systems, and next-generation optical devices. Michael Berry himself once pointed out something elegant. There's a diffraction limit for bright light. You can't focus it below about half a wavelength. But there is no such diffraction limit for dark light. 52 years. That's how long it took to get from Nye and Berry's 1974 theory to Kaminer's 2026 experiment. Half a century for instrumentation to catch up with imagination. And when it finally did, it revealed that darkness, the absence of light, the nothing inside the something, plays by rules we're only beginning to understand. The dark points in a light field are topologically robust, universally present, and now proven to race faster than the waves that create them. Understanding what darkness does when no one is looking turns out to illuminate deep truths about the structure of all waves, and maybe, eventually, about the structure of reality itself. The speed of light is still the speed limit, but the darkness inside it? That was never bound by the rules in the first place.